Welcome! Today we're exploring the fascinating world of quantitative nuclear magnetic resonance, or qNMR. In this session, we'll uncover what qNMR is, how it works, and why it's a game changer for analytical science. Let's dive in. qNMR is a flexible, non-destructive analytical technique. It allows scientists to measure the absolute concentration of compounds in a sample mixture without destroying it. Unlike traditional methods such as HPLC or UV spectroscopy, qNMR detects nuclei directly, giving you precise, reliable results with traceability to international standards. Why does this matter? Well, in research or regulated industries, accuracy and reproducibility are everything. qNMR gives you confidence that your measurements are not only precise, but also SI traceable, meaning they can be tied to the international system of units. Let's look at the advantages that make qNMR so valuable. Absolute quantification. You can measure analyte concentration directly by comparing integrated peak areas without needing a reference standard of the analyte. Versatility. It works across pharmaceuticals, biotechnology, chemical industries, and for a wide range of compounds and sample matrices. SI traceable standards ensures reliability, global standardization, and regulatory acceptance. Non-destructive. Samples remain intact and can be reused, saving cost and resources. Essentially, qNMR combines accuracy, flexibility, and efficiency in one analytical technique. The core principle of qNMR is simple yet powerful. The area under an NMR peak is proportional to the number of nuclei responsible for that signal. By adding a known concentration of an internal standard to your sample, you can compare the integrated peak areas. This ratio allows you to calculate the exact concentration or purity of your analyte. A key advantage here is that you don't need a reference standard of the analyte itself, which is especially useful for rare or expensive compounds. Internal standards, or IS, are stable compounds added to your sample at a known concentration. They serve as a reference point for accurate quantification and help compensate for instrument fluctuations. When selecting an internal standard, you need to consider high purity, usually greater than or equal to 99%, accurate weighing for known concentration, chemical stability, solubility in deuterated solvent, no peak overlap with the analyte, comparable relaxation time for reliable signal integration. Choosing the right internal standard is crucial for accurate qNMR results. Two technical parameters are especially important for qNMR: relaxation time, T1, and T2. This is how nuclei return to equilibrium after an RF pulse. For accurate quantification, you must allow sufficient T1 relaxation between pulses to recover the signal fully. Signal-to-noise ratio, S/N. The quality of your data depends on a high S/N ratio. USP recommends SN greater than or equal to 150 for reliable integration. Poor SN leads to poorly defined peaks, baseline instability, and inaccurate quantification. These parameters ensure your qNMR results are both precise and trustworthy.
How does qNMR compare with HPLC? Both techniques are accurate, but qNMR has several advantages. Absolute quantification without calibration curves. Less affected by matrix interference. No need for analyte reference standards. HPLC, on the other hand, may require multiple calibration points and reference standards. While both methods have their place, qNMR provides a simpler, versatile, and non-destructive solution for quantification.
qNMR finds applications across diverse sectors: drug development and toxicology, monitor metabolic shifts and interactions, metabolomics and bioanalysis, profile metabolites without needing reference standards, natural product analysis, study bioactive compounds, even unknowns. Trace impurity detection, detect low-level impurities more accurately than HPLC. Whether it's drug metabolism, plant extracts, or complex natural products, qNMR provides the precision and flexibility needed in modern research. Regulated industries follow ICHQ 201 guidelines to validate qNMR methods. Validation parameters include accuracy, measured versus true values, with acceptable uncertainty up to 5%. Precision, repeatability among measurements, RSD up to 3.6% for plant extracts. Specificity, distinguishing analyte signals using 2D NMR if needed. Linearity, peak area proportional to concentration, R squared greater than or equal to 0.99. Practical tips include consistent temperature, accurate weighing, optimizing SN ratio, and avoiding sample rotation to prevent artifacts. Finally, let's talk about the future. qNMR is transforming how scientists determine purity and concentration. Regulatory bodies like FDA and EMA increasingly recognize its value. Its applications in pharmaceuticals continue to expand. Impurity quantification, stability studies, and regulatory compliant reporting. The combination of absolute quantification, non-destructive analysis, and regulatory compliance positions qNMR as a cornerstone of modern analytical workflows. As technology evolves, we can expect faster analysis, higher data quality, and even broader adoption across industries.